Okay, yeah, I guess we can start now. Okay, so can you see my screen, and can you hear me also well, I guess? Please let me know if you can't see the screen where it is written like welcome to week 1 of PMRF TA session, or if you can't hear me. Hello? I can see the slides. Can you hear me, or is there a problem? And I can hear you. Okay, you can hear me. Okay. Okay, the recording is okay. I have to just check the recording. The recording is being done. Okay, there's no problem. Okay, thanks. Okay, so welcome everyone to week 1 of this PMRF TA sessions for the NPTEL course Electronic Properties of Materials. So a brief introduction of mine. Let me just zoom it. Okay, so I'm Akshay. I'm a PhD student PMRF in the Solid State and Structure Chemistry Unit SSCU of the Indian Institute of Science IISc Bengaluru, India. Let me just 1 minute. Okay, recording is sorry about that. Okay, so yeah, so we are okay. So my brief introduction. I'm Akshay. I'm PhD student PMRF in the Solid State and Structure Chemistry Unit SSCU of the Indian Institute of Science IISc Bengaluru, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL-PMRF TA for this course, Electronic Properties of the Materials Computational Approach, and we will have total 8 2-hour interactive problem solving sessions every Friday from 7 p.m. to 9 p.m. and they will start from August 25th and will end on October 13th. Because of some unavoidable circumstances, I have to shift the first session from August 25th to today, August 26th. But just keep in mind that from next time, these sessions are going to be on Fridays, 7 to 9 p.m. And if there will be a change like happened this time, so it will be announced. Okay, and also I will also like to announce that feel free to ask any questions that you will have during the session. And also there is discussion forum for this NPTEL course, so I will be active on that discussion forum as well. So if you have any doubts regarding these sessions or any other doubt from the course, then you can just post on those on that discussion forum, and yeah, I will try to solve them there as well. Okay, so now we will start with our problem 1 of the session. Alright, so our problem 1 is so we have to estimate the free electron density in copper and aluminium, and what has been given to us is the mass density of copper, which is 8.96 gram per centimeter cube, and atomic weight of the copper, okay, which is 63.55 gram, and similarly is given for aluminium as well, mass density and atomic weight. Okay, so here we just so yeah, so let's solve this problem. So here we are given mass density. So basically what we are given, we will denote mass density rho of m, and by rho of m in gram per centimeter cube, right? And weight, so basically what is this atomic weight? So it is basically weight, if I say weight of 1 mole, so that is denoted by this A gram, that will be equals to A gram, where A will be our atomic weight in gram. So that is given to us for both copper and aluminium. Atomic weight in grams, right? Now here we know that 1 mole is equals to Avogadro number, which is equals to 6.02 into 10 to the power 23, and we can denote this by Na. Alright, and so weight of one atom from this here, so like we have the weight from this atomic weight, we have the weight for Avogadro numbers of atoms, which is 6 into 10 to the power 23. So the weight of one atom will be given by this A divided by Na, Avogadro number, in grams. So that will give us the weight of this. Alright, so now and we also have this mass density, which is the weight per unit volume. So from here, now we have the weight of one atom and we have mass density as well. So we can write number of atoms per centimeter cube, that will be equals to rho of m divided by this A divided by Na, which is the mass of one atom. Okay, so mass density divided by mass of one atom, that will give us the total number of atoms per centimeter cube. Now let's say we know the number of valence electrons, which will be basically our conduction electrons. So we have to find the number of estimate the free electron density. So we need to find the number of free electrons per unit volume. So that will be valence electrons will be the electrons that will be free from the core shell, and they will basically contribute to the conductivity of these systems, and they will contribute to free electrons. Only those will contribute. So let's say that is the number of valence electrons. We are denoting it by Z. Then the number of valence electrons per centimeter cube, that will be equals to, that it will be our electron density that we have to find, that we can give by Z rho m, which is the number of atoms, times this Z, number of valence electrons. So that is Z is the number of valence electrons from each atom, divided A by Na. Right, so what we will get here is N is equals to Na Z rho m divided by capital A. Right, so this is the formula that we have derived for our electron density. Now we will solve our for a particular case of aluminium and copper. Now for aluminium, okay, let's start. Okay, so for copper, okay, for copper, rho m, that is given to us as 8.96, okay, gram per centimeter cube. Alright, that is the value that is given to us. And capital A, its atomic weight is given as 63.55 gram. Alright, and our Z is equals to 1. For aluminium, for copper, Z will be 1, number of valence electrons. So our free electron density, so let me just denote it. Okay, we know this N is basically our free electron density. This is our free electron density. So N for copper, that will just equals to, just we just have to put this value. So for using this formula, so what we have is 6.02 into 10 to the power 23, which is the Avogadro number Na. Z here is 1. Rho m is given to us 8.96 divided by our capital A, which is 63.55. Alright, and this will be per centimeter cube. This you can check, it is because 8.96, it is gram per centimeter cube, and then A was also in gram. So in the denominator we will have gram, and in the numerator we will have gram per centimeter cube. So gram we cancel out, so the unit will be per centimeter cube. And if you calculate it, then that is just like just a calculator or something. So the value that you get is 8.49 into 10 to the power 23 per centimeter cube. So this is our free electron density for copper. Okay, and then we will go for aluminium. So what we have for aluminium, we have rho of m is equals to 2.7 gram per centimeter cube, and capital A equals to 26.98 in grams. Okay, and for aluminium, Z we know is will be number of valence electrons will be 3. Again, we just have to put values in the formula that we have derived. So that will be Na will be 6.02 into 10 to the power 23 times Avogadro number times the Z, which is 3 in this case, times this rho m, mass density, which is 2.7, divided by capital A, which is going to be 26.98. Alright, and this will also be per centimeter cube. So our N of aluminium, if you just calculate this, then that will come as 18.1 into 10 to the power 22 per centimeter cube. So this is our answer for copper and for aluminium. So you can see that for copper, the free electron density is 8.49 into 10 to the power. Okay, it is 10 into 10 to the power 22 actually. Yes, sorry, my mistake. This will be 10 to the power 22. 8.49 times 10 to the power 22, and for aluminium it is going to be 18.1. So from this thing, what we have concluded, one conclusion that we can make is, let's make a conclusion, that is number of free electrons in aluminium is 2.1 times the, okay, 1 minute, I guess someone, sorry about this, someone wants to join. Okay, so we have calculated the free electron density for copper and aluminium, and we can now we can see that aluminium has a higher free electron density compared to copper, and it is actually 2.1 times approximately higher than copper. So we can conclude from here, let me just 8.49 and 18.1, that number of free electrons in aluminium is 2.1 times the number of free electrons in copper. Yeah, this lecture is being recorded actually, so you can see the solution again on YouTube in the recording of this lecture. Okay, so like we have to solve a lot of problems, so I cannot go there, I cannot go back and do this. Okay, yeah. So this lecture is going to be this is being recorded, so you will get the recording link as well, so you can watch all these solutions again as well. So if you miss something because of network issues or something, then that's fine, you can go, and if you have any doubts, then you can ask in the discussion forum of the course or in the next session as well. Okay, and 2.1 times the number of free electrons in copper. Alright, so this is a basic question, so I hope there is no problem in this one. Alright, so let us just go to problem number 2 now. Okay, so now in problem number 2 is estimate the volume per conduction electrons for copper and aluminium. So in problem 1, what we did is we find the free electron density for both copper and aluminium, and now in this problem we have to estimate the volume per conduction electron. What is the volume for each conduction electron? So that is also useful most of the time. And okay, so for this, let me just go back. Okay, so we have N, which is the number of conduction electrons. This we have already calculated in our previous problem, number of electrons, conduction electrons. Per centimeter cube. Okay, so if we have number of conduction electrons per centimeter cube, then what would be 1 by N then? So 1 by N will just be it will be our answer that you want. It will be the volume of one conduction electron. Sorry, one conduction electron. Alright. Alright, so I guess this is clear. Like we have number of conduction electron per volume, and if you just reverse it, so it will be the volume of one conduction electron. Volume divided by the sorry, number of conduction electron. Sorry, just wait a minute. Okay, sorry about it. I'm having a little scratchy throat. Okay. Okay, now, so this is clear. Okay, so like we have calculated the free electron density, and if we want to find the volume of one conduction electron, so that will be just 1 by n, which is volume of one conduction. That will be like total volume divided by the total number of electrons. Okay, now we can solve it like this, or there is something important, like we would like to find the radius of the electron. Basically, what is the volume of, we are saying that, okay, so electron is same, but the volume that is being occupied by electrons in different materials, that we will see that will be different. So to really quantify it, we will try to find the radius of that volume. Okay, so you can use this 1 by n as well, or we can go ahead and find the radius. If we consider that electrons are basically they are making a volume of a sphere, so we can calculate the radius of that sphere. So we can solve the problem from here as well, or we can first just find this radius as well of the sphere that the electron will be forming. So we will assume that the volume to be spherical, that the volume that is being occupied by each electron, and we say that with radius of Rs, and we can write then (4 by 3 pi Rs whole cube). Okay, so that will be equals to 1 by n, and from here you can find this Rs, which is basically the radius of the volume that is being occupied by the electron, 3 upon 4 pi 3 upon 4 pi n whole to the power 1 by 3. Alright, so this will be the formula. So we have found this formula. Now we will find this Rs. Now so in this formula the only parameter we have is only variable we have is n. So we can find Rs for copper. We know that will be 3 upon 4 pi n of copper whole to the power 1 by 3, and we have calculated n of copper, so just put that value here, and let me just do it so that just one I will do. So for 3.14 into it was n was 8.49 that we calculated, n of copper 8.49 into 10 to the power 22. Okay, it was centimeter cube. Okay, so it was per centimeter cube, n is per centimeter cube, n of copper was 8.49 into 10 to the power 22 per centimeter cube, and it is 1 by 3, so this will come in units of centimeter. Okay, because centimeter cube will go up and 1 by 3, so the unit will be centimeter. And to solve this kind of problem, then we can see that, okay, so what we can do is 22, we know that to divide it by, to get it out of this, we need to multiply it by 100, so it will become 10 to the power 24, which will come out as 1 upon 10 to the power 8 or 10 to the power minus 8. So if we do that, we have to multiply 100 on the denominator and 100 in the numerator. So that is just a mathematics trick. So 403.14 into 8.49, alright, whole to the power 1 by 3 times 10 to the power minus 8 centimeter. Alright, so that is just to get this 10 to the power 22 out of this bracket, and we know that 1 angstrom is equals to 10 to the power minus 10 meter or 10 to the power minus 8 centimeter. So 1 angstrom is equals to 10 to the power minus 8 centimeter. Let's write it here. Okay, so let's see if someone has to join. Sorry, So you can do this calculation, and what you will get is Rs of copper will be is equals to 1.41. Okay, this will 10 to the minus 8 centimeter will become angstrom. So what you will get is this radius of electron in copper will be equals to 1.41 angstrom. Alright, and then for aluminium, you can then solve for aluminium. We have n of aluminium equals to 18.1 into 10 to the power 22 per centimeter cube. Alright, Rs of aluminium, that will be equals to, again just put all the values, 4 into 3.14 for pi, and 18.1 into 10 to the power 22, 4 to the power 1 by 3 in centimeter. And again you can just do the calculation, and what we will get is 1.09 angstrom. Alright, so this we have calculated. And then so basically if I divide the volume of the electron in the aluminium divided by volume of electron in copper, so that will be, that as we have seen that it could be written as N of copper and free electron density of copper divided by free electron density of aluminium, or it could be written as Rs of aluminium whole cube divided by Rs of copper whole cube, which will be 1.09 divided by 1.41 whole cube, which if you calculate, it will be approximately equals to 0.46. Okay, or approximately you can say 0.5. Alright, so here again we can make a conclusion. Alright, conclusion. Okay. So one free electron in aluminium occupies half the volume compared to copper. Alright. Okay, so this is our problem number 2, where we have find this estimated the volume per electron in copper and aluminium, and we have find that the one free electron in aluminium occupies half the volume compared to copper. Alright, now we will go to problem number 3. So we will solve, actually I should have announced it earlier. So yeah, we will solve like 10 problems, 10 theoretical problems, and I'm starting with this basic problems. So these are like basic problem Drude models, and we will go to a problem in Drude model as well from Ashcroft-Mermin. And after that we will also go into some problems in quantum mechanics of infinite potential well, and afterwards we will have our programming, the coding section, where I will do a Python tutorial, and also there will be a problem similar to infinite potential well in the video lecture. We will solve it for the symmetric potential. Yeah, I should have mentioned it in the starting of the session. Just to yeah, from next time I will just brief you like what you are going to see in the sessions. Okay, so again let's do one more simple question. Okay, so now we have to estimate the volume per atom or molecule for the ideal gas. Okay, so for ideal gas we know that okay they will not interact, so we don't consider any valence electron or anything. We just have to estimate, in this question we just have to estimate the volume per atom or per molecule. Now earlier we have found the volume per electron. Now for this again now it is given that we have been given something which is the volume of 1 mole of ideal gas. So basically these questions are also actually giving you some idea of the numbers for the real materials. So from this basic estimations, this classical estimation, what are the numbers for different elements. Okay, now we will estimate the volume per atom or molecule for the ideal gas. So we are given that volume of 1 mole of ideal gas is 22.4 liter. So what does it mean? So volume of 1 mole of ideal gas is already given to us, which is okay, which is equals to 22.4 liter, which is in centimeter cube is given by 22.4 times 10 to the power 3 centimeter cube. Right? So the number of molecules Okay, so in this volume, for like it is a volume for 1 mole of ideal gas, so we know that number of molecules are the Avogadro number. Check if there is a message or something. Right. Okay, so the number of molecules will be Avogadro number, which is 6.023 into 10 to the power 23. Now n of I will be equals to, so it is the number of ideal gas, number of ideal gas molecules, you can say molecules or atoms per centimeter cube. Alright, so ni will be equals to total number of we need to find per centimeter cube. So we know that in this volume, in 22.4 into 10 to the power 3 centimeter cube, which is the volume of 1 mole of ideal gas, we have Avogadro number of molecules 6.022 into 10 to the power 23. So per centimeter cube it will be 6.02 into 10 to the power 23 divided by the total volume, which will be 22.4 into 10 to the power 3, and we can calculate it to be 2.7 into 10 to the power 19 per centimeter cube. Okay, so this will be our answer. Answer is like, okay, we have to estimate the volume per atom or molecule. So this is the number of ideal gas molecules per centimeter cube. So from here we need to find what is the volume of a molecule now. So that will be, as we have seen for electron, it will be now similar for ideal gas, it will be 1 by Ni. That will be equals to 3.7 into 10 to the power minus 20 centimeter cube. Okay, so this will be the volume occupied by each molecule of ideal gas. Right, that's our answer. And again, similar to what we have done for the electron, you can do 4 by 3 pi Ri cube equals to this volume 3.7 into 10 to the power minus 20, and from here we can do the calculation for Ri. So I will, for the sake of time, I will not do this calculation. So you can just Ri whole cube, and this Ri will just be equals to 3.7 into 10 to the power minus 20 times 3 divided by 4 pi whole to the power 1 by 3 in centimeters. Okay, because this is in centimeter cube, 1 by Ni. So this is basically equals to 1 by Ni, 4 by 3. Okay, this is the volume of a molecule. So similarly for the electron, we find Rs, we can find this Ri, which is the volume of this ideal gas molecule. Alright, and this Ri, if you calculate, it will come as 21 angstrom. Okay, and remember, okay, so when you will get this answer, remember that 1 angstrom is equals to 10 to the power minus 8 centimeters. So you have to do this conversion to get to angstrom. Alright. Okay, so here also we can get some conclusion. So we are getting, basically from this number we are getting conclusion for the real systems, what happens. So one ideal gas molecule, so you can see that basically this Ri is 21 angstrom, which is, okay, there is some, sorry about that. Okay, so as you can see, this Ri is 21 angstrom, while what we calculate for the electrons, it was like 1 angstrom around. So we can say that one ideal gas molecule, so from here we can say that, okay, one ideal gas molecule occupies volume equivalent to 4 by 3 pi this Ri cube, which is 21 cube angstrom cube. Alright, and one conduction electron occupies volume equivalent to, now we can approximate the values that we have is like 1.09 or 1.41 angstrom, 1.09 angstrom, so around 1 angstrom we can say. So it is around like 1 angstrom whole cube the conduction electron occupies. So you can see that 21 whole cube, it is quite large. So this is like one ideal gas molecule occupies a large volume compared to one conduction electron. So from here what we can see is that free electron gas is very densely packed compared to ideal gas. It is this it is the same that we have done earlier question. It is 4 by 3 pi rs whole cube. So this rs value this rs value we calculated in our previous problem, in problem number I guess in 2. rs value, so you if you remember, like rs value in aluminium was around 1.09 and for copper is 1.41. So we can approximately say that this radius for conduction electrons comes around 1 electron volt. Right. Alright. So this rs. So basically this. So here we can see that the volume that is being occupied by this conduction electrons is very small compared to what will be occupied by an ideal gas. Atoms you can say because they don't form molecules, so you can say they are atoms. So that's why from this we can make a final conclusion that free electron gas that is very densely packed compared to the ideal gas. So if you are in a system, in a box, if you have this ideal gas, which we know are non-interacting, the ideal gas don't interact with each other. I should have written molecules. I should have just written atoms actually. So you can just correct it. I've written molecules somewhere. So instead of, if you just consider these free electrons in these metals, that is very densely packed compared to this ideal gas for the same volume. Alright. Okay, so let's just go to now problem number 4. Alright. So now in problem number 4 we have some real experimental data. So like we have like resistivity of copper in micro ohms centimeters. This is resistivity, not resistance. It is micro ohm centimeters at 3 different temperature values in Kelvin. So we have rho at 77 Kelvin 0.2, and rho at 273 Kelvin 1.56, and rho at 373 Kelvin 2.24. So now from looking at this data, can we assume that the resistivity increases linearly with temperature or not? So that is our problem, like if we can assume it or not. So how are we going to check it? So if we have to do this kind of problem, then we will just first assume that, let us assume that our rho, which is if it is a function of T, resistivity is a function of temperature for a system, then we can assume that it is, let's say it is approximately equal to some alpha times T. Okay, so we have to assume how the resistivity is changing. We are saying we just want to check if it is changing linearly or not, and given this 3 data points. So one way will be, okay, so let's just assume that it will behave like that. It will increase linearly with temperature. So then I can write my this resistivity as approximately as some constant alpha. So this alpha is just some constant. Times T. So I can assume it is this, so it is linearly. Then in that case I can say that my rho T divided by T, that will be approximately some alpha. Okay, that will be some constant, And so that is what I can say, that for some temperature T1 by T1 divided by rho of some T2 by some temperature T2, this should be approximately 1. Okay, so if it is, even if it is approximately coming 1, then I can say that okay, then so this will happen, this thing will happen. So we obtain this when we assume that resistivity is changing linearly. So this will happen if resistivity depends linearly on temperature T. Alright, so we just want to check, and there could be like square as well, like someone, maybe there are some values and we want to check more values and someone wants to check some alpha T square, so we can maybe go in the similar fashion. But for linear, just to check the linearity, it is much easier, as you can see. So if you want to check like if this condition is being satisfied for these 3 points or not that are given to us, these 3 data points. So first we can say that rho of 273 divided by the temperature 273, temperatures are in Kelvin, and divided by, I will check rho of 77 by 77. Okay, so we are going from 77 Kelvin to 273 Kelvin. So is this linear or not? So this is 1.56 divided by 273, and this will be 0.2 divided by 77. So this comes as 2.2. So 2.2 is quite large compared to 1. So based on this 3 data points, we can say that from, if we go from 77 Kelvin to 273 Kelvin, the just 1 minute. So yeah, if we go from 77 Kelvin to 273 Kelvin, the change in resistivity doesn't seem to be linear. So it would have been linear if this ratio, ratio that we have calculated, it was close to 1, but it is 2.2. So we can say that from 77 Kelvin to 273 Kelvin, it is not linear. And but let's just check for rho at 373 Kelvin. So now we are checking from 273 Kelvin to 373 Kelvin, what is the case. So rho at 373 is given as 2.24 divided by 373 and 1.56 divided by 273, and if we calculate it, this comes as 1.05, which is very close to 1. So now we can say that since it is coming very close to 1, and this is what we should have got if the trend from T1 to T2 is linear. So we can say that okay, from 273 Kelvin to 373 Kelvin, it seems like the resistivity must be changing linearly, but not from 77 Kelvin to 273 Kelvin. Okay, so again we can make a conclusion here that near 273 Kelvin we can assume linear temperature dependence of resistivity. Okay, and that why we can assume, because we can see that from 273 Kelvin to 370 Kelvin, this ratio is coming very close to 1. So we can assume that it is linear temperature dependence of resistivity near 273 Kelvin, but not near liquid nitrogen temperature. Which is 77 Kelvin. So since from this ratio is not close to 1, so we can assume that from near 77 Kelvin, maybe resistivity is not changing linearly. And this liquid nitrogen temperature is quite interesting because basically there are very exotic phenomena that can happen in materials. But most of the time some of magnetism or superconductivity. But as you know that if you go to higher temperature, there are thermal fluctuations because of which this magnetic ordering of spins is disturbed, so we don't get that magnetism, and there is some Curie temperature, and superconductivity that is also observed at low temperature. So finding some properties, and liquid nitrogen temperature is interesting because liquid nitrogen, this 77 Kelvin, it is not that difficult to obtain in the experiments. So just like quick interesting fact about this temperature. So if you can find any phenomena happening in materials and you can make it sustain at 77 Kelvin, then that could be done in an experiment much simpler, like it will be simpler. So liquid nitrogen temperature is simpler to get in experiments. Alright. Okay, now we will go to problem number 5. So this problem number 5 is from chapter 1 of this book, Solid State Physics by Ashcroft-Mermin. Right, this book. So this is a very very nice book for solid state physics, and you can say mainly condensed. It is the book is solid state physics. So yeah, you can say solid state physics and condensed matter physics are quite similar. So it's a very nice book. So you can check out for this topics on Drude Model, and also later on in the course there will be electron density and all band structure calculation. So for solid state part you can refer this book, Ashcroft-Mermin. And right now we will solve this problem from this chapter 1. And in this session I am planning to just solve the first 2 parts. It is actually I found that it's a very big problem, and there are many other problems that we have to solve, and we have this coding session as well, and we are running out of time, like only 40 minutes are gone. So yeah, so in this session we will just solve the first 2 parts, and if we will get time, then we will solve the rest of the parts after completing everything else, or we will solve those C to E part in the next session. Okay, so let's just go to this problem. So in the Drude model, we know that the probability of an electron suffering a collision. 1 minute. क्या बंद क्यों नहीं कर रही थी आप लोग? बंद क्यों नहीं कर रही थी? Okay, yeah. Okay, let's just come back to this problem. So in Drude model, we know that the probability of an electron suffering a collision, okay, this probability of electron suffering a collision in any infinitesimal time interval dt is just dt by tau. Okay, so where tau is our relaxation time. So now the question is asked is, in the first part, show that an electron picked at random at a given moment had no collision during the preceding t seconds with probability e to the power minus t by tau, and show that it will have no collision during the next t seconds with the same probability. Okay, so in the next t seconds also this probability will be c. So let's just solve it. So let us solve the first part. So we have to show that if we pick an electron random at a given moment, and so we have to show that the probability that it had no collision during the preceding t seconds, it will be e to the power minus t by tau. So now solve it. So let's start from the beginning. What all we have now, according to the Drude model, the probability of an electron suffering a collision in any infinitesimal interval dt is dt by tau. That is given in the question, and our tau is our relaxation time. So I'm just writing it. What we have, we are given relaxation time. Alright. So what we can derive from this is the probability of an electron suffering no collision. No collision. Okay. So we are seeing that if the probability of collision is dt by tau, then the probability that the electron will not suffer any collision in an infinitesimal time interval dt, that will be given by 1 minus dt by tau. Okay, so it will either collide or either it will not collide. So this probability will be 1 minus dt by tau. Now let's go to our part A. So it is asking like now to determine the probability of no collision during the preceding t seconds. Okay, so we need to find this thing during t seconds. We first divide. So how we will find it? We first divide the preceding t seconds the t we okay, no, I am ready. We divide the t second or time t. We divide the time t into n intervals such that delta of t will be equals to t by n. Alright. So what we are doing is to determine this probability that there is no collision during the preceding t seconds, and we know that for what were the probabilities that we can get is for a very infinitesimal time interval. So what we'll do is we will divide this from 0 to t. We will divide it into n parts. Okay, we will divide it into n parts, and each part will be equals to t by n, and there will be n sections, you can say, from 0 to t. So we are dividing it by this, and our delta t, this is equals to t by n. Now if we say for n tends to infinity, now if we divide it and our n sections, right. If we say n is tending to infinity, okay, then we have limit n tends to infinity of delta t, that will be our dt, the infinitesimal time interval that we for which we know the probabilities. Okay, for which the Drude model has given us the probability. You can say it is very small value. Okay, so very small value or infinitesimally small value, you can also say. Now, so probability that no collision occurs in time interval delta t is given by, so this will be given by 1 minus delta t by tau. Alright, so that is from this Drude model. So we know that probability of electrocollision, if there is no collision, that is 1 minus dt by tau. What we did was we need to find it like for preceding t seconds, it will not happen. So what we did is we divide that 0 to t among n sections, and each section then will be delta t will be equal to t by capital N, and if n tends to infinity, then this delta t is basically our infinite time dt, and for that dt we know that the probability that no collision will happen in this delta t time. Now I can say that it is 1 minus delta t by tau. That is given from the Drude model. Alright, so so I guess there is no problem up to this point. Now we note that the probability for no collision in interval delta t must hold for each time interval delta t making up time t. Alright, so basically what we have to do is we need to find a probability that from 0 to t for all this time there is no collision, and we know that for delta t what is the probability of no collision, and to find a probability that from 0 to t there is no collision, what we want is for each of these delta t there should be no collision. Okay, so that is clear, like there should not be any collision for each of these delta t. Alright, and therefore therefore the probability, I will denote it by P of t for no collision during the interval 0 to small t can be written as multiplication of probabilities 1 minus delta t by n for each n intervals. Okay, so okay, so basically for each time we want that for each delta t there should be no collision. So the net probability that there will be no collision from 0 to t will just be the product of this 1 minus delta t by n. Right, so that is, so our probability pt, so this is our probability that there will be no collision from 0 to t, that will be given by 1 minus delta t by this 1 minus delta t by n times 1 minus delta t by n, and so on up to n times. So this will be n times multiplication, so we can get this pt will be equals to 1 minus delta t by n whole to the power n. Alright, now what we have to do is substitute delta t equals to t by capital N. Okay, so we will substitute now delta t with its definition, which is t by n. So our probability pt, so we are doing this because we want the answer in terms of, we want this probability in terms of t, so it will be 1 by t n square whole to the power capital N. Alright, okay, so 1 minute, did I make, oh sorry, I made a mistake here. So the probability was 1 minus delta t by tau, yeah. So probability that we have from Drude model was for no collision 1 minus dt time interval divided by tau, relaxation time. I accidentally wrote it n. Okay, so this is 1 minus delta t by tau, and so so we have to multiply this for each of these intervals that we have divided. So it will be 1 minus delta t by tau n times, so it will be 1 minus delta t by tau to the power n. Alright, so the probability that there will be no collision, that will be given by 1 minus delta t by tau whole to the power n. Now we will replace this delta t by n, so we will have 1 minus t by tau times n whole to the power n. Okay, I hope this is clear. Okay. Yes. All right. So now we have this probability. So now we know that we have taken we consider that this is n is tending to infinity. These are infinite sections we have done from 0 to t. Now for n tends to infinity, this p of t will become limit n tends to infinity 1 minus t by tau n whole to the power n. Okay. Now let us consider that minus x is equals to minus t by tau. This is just x equals to minus t by tau. So our probability p of t comes as limit n tends to infinity 1 minus t by tau is x. It will be x by n to the power 1 plus, we have considered x equals to minus t by tau. So it is 1 plus x by n whole to the power n. We limit n tends to infinity. Now we know this, we know that limit n tends to infinity 1 plus x by n, okay, to the power n, that is will be equals to e to the power x. Okay, so let me just prove it as well, and I'll just prove it with a different color. Okay, so now proof for this. So what we will do is we will write to prove this. Okay, this is something that is quite common, like limit n tends to 1 plus x by n whole to the power n equals to e by x. But let me give you the proof as well. So write to prove it, you have to write 1 plus x by n whole to the power n. Now this could be written as e to the power n ln of ln of 1 plus x by n. Okay, I hope this step is clear. Okay, it is exponential to the power n ln of 1 plus n. So you can make this n go into the ln. So it will become ln of 1 plus x by n whole to the power n. And then you can replace this e by ln. So it will be ln e of 1 plus x to the power n whole to the power n whole to the power ln of e. So which will be 1. Okay. So I hope there is no problem in this step, going from 1 plus x by n whole to the power n to e to the power n ln of 1 plus x by n. Okay. If you have any problem in one of these steps, then please let me know. If you are confused or if there is some problem, then you can stop me and ask. Alright. Alright, so now we have this. Now since ln of 1 plus t, okay, now how ln of we know that if we have ln of 1 plus t, so it goes as t plus order of some t square when it is I guess I should have written ln of 1 plus x, or you can say, okay, t when t tends towards when t tends towards 0. Okay, so this is, we know that, okay, if you have ln of 1 plus t, if you have seen this function, then it actually goes with the t plus order of t square when t is tending towards 0. So it is linear around t, and we can see that our t could be x by n, and as n is tending towards infinity, x by n is also tending towards 0. Right. So we have n ln of 1 plus x by n, and okay, so we have here n of ln of 1 plus x by n. So since n is tending towards infinity, this x by n is tending towards 0, so I can write this as ln of 1 plus x could be written like this. So I can write ln of 1 plus t could be written like this. So I can write it as n times x by n plus some order of x by n square, and these terms could be neglected. Okay, neglect very small. Okay, so they are going to be like x by n is already going to be very small, and then x by n whole square values would be very small. So this order of square values we can neglect. So now from here, what we'll have, we have to find limit n tends to 1 plus x whole to the power n. Okay, we needed to find limit of this 1 plus x by n o to the power n. Then we write this thing as e to the power n ln of 1 plus x o to the power n, and then we find as this n ln of this thing, this could be written as n times x only. So we can write this thing as limit n tends to infinity e to the power, now ln of n plus x by n could be written as n, and this could be written as n times nx by n. Okay, so basically n let me just check. Okay, limit n tends to infinity 1 plus x divided by n. Yeah, this is some x. Okay, this is some x times. Sorry, this is, there will be no n. Okay, yeah, I was getting confused. Sorry. Yeah, so we have written this n ln of this. So you can approximately return as, if you make this x in here, so we neglect this terms, and n will get cancelled. So it will be approximately some x times some order of these values which we will ignore. Alright, so it will be approximately, you can write this thing as x now when n is tending towards infinity and tends towards infinity. Alright, so n ln of 1 plus x to the power n, this could be approximated to x. So we have here e to the power x, and there is no n now, so it will be x, e to the power x. Or actually, just write, okay, so as n tends to infinity, this term is going to x, so it means we are getting e to the power x. Alright, so that is what we have written. The limit of n tends to infinity 1 plus x to the power n, that will go to e to the power x, because this n ln 1 plus x to the power n, that goes to x as n tends towards infinity. Alright, I hope this is clear. Okay, if you have any doubt, then you can just stop me and ask. Alright, so now we know this limit, so now we are very close. So now we know this probability is just this limit. Okay, so the probability we had is limit n tends to infinity 1 plus x by n o to the power n, and we have found that this limit is just e to the power x. Alright, and here our x we have taken as minus t by tau. So our p of t comes as e to the power minus t by tau, and that is what we had to prove. So here so therefore we can write as the probability that when an electron is picked at random, it did not suffer any collision during the preceding t seconds is p of t is equals to e to the power minus t by tau. Okay, alright, this is done. Alright, this is part A. Now for part B, let me just check if this is okay. Now let us quickly do the part B as well. It is already 8 p.m. Okay, we are a little behind the schedule. Okay, now part B is that show that the probability that the time I hope you can see the part B. Show that the probability that the time interval between two successive collision of an electron falls in the range t and t plus dt is this. Okay, so now what we have to find is, so first we found in part A that if we pick at any time t, the probability that there was no collision from 0 to t, that probability was e to the power minus t by tau. Alright, and now what we have to find is that we have to find the probability that time interval between two successive collision, like one collision happens and then the next collision happens. collision of an electron falls, that will fall in the range from t to t. So the probability that the collision will happen between t and t plus dt, it will be given by e to the power minus t by tau dt by tau. Okay, so now we are saying that the collision will happen. So the collision doesn't happen till time t, and now the collision happen at time t plus dt by tau. Alright. So now for that, the probability that an electron hit at random does not collide in interval zero to t, and then thus collide in the next interval dt, which is a very small interval, collide interval dt, and then thus collide in the next interval dt, can be calculated by multiplying the probability of collision in interval dt with the probability pt. Okay, so probability p of t we have found is that it is the probability that there was no collision from time 0 to t, and then you have to find that the probability that an electron picked at random does not collide in interval 0 to t, and then thus collide in the next interval dt. It can be calculated by multiplying the probability of this collision in interval dt with the probability p of t. So basically what we are saying is this p of capital T. Okay, so what we are saying is we want two things. First, we doesn't want there should be any collision up to time t seconds. So for priority for that was small pt, and then we want the collision to happen at in time interval dt. So that we know from Drude's model. Okay, from Drude's model we know that if for the priority that the collision happens in time in interval dt, that will be dt by tau, and so the priority that there will be no collision from 0 to t, and then there will be a collision in interval dt, that will be given by pt times dt by tau. Alright, so that pt will be equals to e to the power minus t by tau, a small pt, this is small pt that we have calculated, times dt by tau. So here we have obtained our pt. So this is what we have to find, e to the power minus t by tau dt by tau. So this is what we had to find. So this is the probability that there will be no collision from 0 to t, and then there will be a collision at dt. Let me just write it down. This is the probability that an electron picked. Let me just write it in somewhere or something. Probability that an electron picked at random does collide does not collide in interval 0 to t, and then thus collide in interval dt. Alright, so this is the probability that we had to find, and we found it by multiplying this thing where this pt, this was the let me just write it here. Pt was the probability that an electron picked at random suffers no collision in interval 0 to t. Alright, and this probability, this is probability of an electron suffering a collision in an interval dt, which is a very small time interval. Okay, so by multiplying this probability that there is no collision from 0 to t and then there is a collision at dt, we get the probability that an electron picked at random, it will not collide interval 0 to t, and then it does collide in interval dt. And we just have to multiply the two probabilities. Alright, now for the sake of time, like it is 8:11 already, so we're not gonna solve this the remaining C to E part. Most probably I will solve those in the next session. Alright, so let's do some questions, and so now next 5 questions, they are going to be in quantum mechanics, and mostly for the infinite potential well problems, so they will help you with the assignments. Okay, now let's start with the problem number 6. Now the problem is a particle is confined in a one-dimensional infinite potential well, particle in a 1D box. Okay, so it is a question on particle in a 1D box. Now the first excited state energy of the particle is 4 electron volt. Now it is asking us what is the ground state energy. Alright, alright. Okay, so we have to, so what is given is that we are given that the energy of the first excited state energy that is given to us, it is 4 electron volt, and now we have to find the ground state energy. It is asking us what is the ground state energy if the system is a one-dimensional infinite potential wave. The problem is of a particle in a 1D box. So for this we know that for a particle in a 1D box of length L, E of n will be is equals to n square. So this energy of the nth state, n is our quantum number, so it will be n square h5 square pi square by 2ml square, which let's say we can denote as n square times E naught. So I'm saying this h5 square pi square is over here, this E naught is equals to h5 square pi square by 2ml square. Alright, so yeah, so all the problems are going to be infinite square wave. So in this problem I will just explain what m and everything is, and for the rest of the problem I guess that will be obvious. So here m is our mass of particle, and n will be equals to, it will go from 1, 2, 3 and so on. It starts from 1, and that is our basically quantum number of the particle. Alright, so we have this is our n, and m is our mass of particle, and En is n square h5 square pi square by 2ml square, that we know for a particle in a box. Now so what is our first excited state? Now our first excited state will be, when you say it is our first excited state, it means we are saying that n is equals to 2. Okay, so n equals to 1 so n equals to, so what is our ground state? Our ground state is n equals to 1. So our ground state is n equals to 1, and when we say which is our first excited state, so that will be the next state will be n equals to 2. So that will be our excited state, and our ground state will be n equals to 1. So yeah, so our ground state is given by n equals to 1, and so the first excited state, it means when we are saying it is the first excited state, it means it will be n equals to 2. Alright, so we are given that energy of, so it means energy of first excited state that will be equals to E. For n equals to 2, it will be E2, and if we put 2 here, so we know that our energies are basically n squared times E naught, so 2 square will be 4, so E2 will be equals to 4 times of E naught, and it is given in the question that this first excited state is 4 electron volt, and we are asked to find what is if the first excited state is 4 electron, what is the ground state energy. So 4 E naught, and that is equals to given as 4 EV. So from here we can find that E naught will be equals to 1 EV. Okay, or let me just so this will be 2 square times E naught, 4 times of E naught, and this is given in the question, it is given as 4 EV. So our from here I can find E naught will be equals to 1 EV, right? And now the question is asked, what is the energy of ground state? Now ground state energy, that will be equals to 1 square of E naught, and that will be simply E naught, and that is given to us as that we have found is 1 EV. So here we have found that if the first excited state is 4 EV, then our ground state is coming as 1 electron volt. Alright, now let's go to problem number 7. It's 8:17. Okay, the problem number 7 is the ground state energy of a particle confined in an infinite potential well. Again, the particle in a 1D box length of length L is E1. Okay, so for the potential where the length of the well, this length of the L, width of the L, you can say width of the well, that is L, then the ground state energy is E1. Now what is the first excited state energy of the same particle if it confined in an infinitesimal potential well of length 2L? Okay, let me see this one. Alright, so we need to find this first excited state energy if the length of the potential well is 2L. Okay, now again we know that for, again I will just say for particle in a 1D box, of length L, so I'm saying the length is L. I know E of n is equals to n square h phi square pi square divided by 2ml square. Alright, and where we know what is m and what is n. Now so here it is given that, okay, so ground state energy, so it is given that the ground state energy is E1. So the ground state energy for length L, that is given as E1, and then that will be equals to n, will be for n equals to 1, it will be 1 square times this again, okay, let me just again write this as some n squared times E naught, where E naught is this value, just to make things simpler. So this is equals to E naught. Alright, so just to write things fast. Alright, so this will be 1 times E naught, so what we have is energy E naught. Alright, so our E1 value is just basically E naught. Now for a particle for particle in a 1D box, or for the same particle we are seeing, so just for particle in 1D box of length, of length 2L, okay, of length 2L. Now our E of n will be given by n square h phi square pi square by 2m. Now instead of L we will just write it as 2L whole square. So now what we will get is n square h phi square pi square by 2 square 4 8ml square, and in terms of E naught I can write this as n square by 4 E naught. Alright, because E naught is h phi square pi square by 2ml square, so I can write it as n square by 4 times E naught. So this is the energy. And now what has been asked is what is we have to find for this system with n2L, we have to find the first excited state energy. Now for first excited state, as we have seen, the first excited state, when we say it is a first excited state, we mean n is equals to 2. We meant n is equals to 2. So okay, so for the first, when we say it is first excited state, we meant n is equals to 2. Alright, so it means the first excited state energy for length 2L, that will be equals to E of 2, and I have denoted by E of 2, that will be equals to 2 whole square divided by 4 times E naught, and that you can see is actually equals to E naught. So what is happening here? So now, so what we are getting is E2 is equals to E1, where this E2 is the first excited state for length 2L. Okay, I will just write it short, for length 2L, and this is the ground state for length L. So what we can see that basically if we double the length, then whatever our first excited state energy will be now, so that will be equals to the ground state energy if the length was L. Wait, 1 minute. Sorry about it. Okay, yeah, so we have, so this is an interesting thing. So basically if we increase the length of this potential well, then our energy level, the value of the energy levels will start to decrease. Alright, and here we have seen that if we have just double the length, then our first excited state energy, that will become to the energy of the ground state if the length was L. Alright, so this is our problem number 7. Now problem number 8. So we have to determine the de Broglie wavelength for a particle confined in a box of length L, and it is in the third excited state. Okay, so now we are saying that a particle is in again in a 1D box, and it is in the third excited state, and we need to find its de Broglie wavelength. Okay, so again we have En. We know En will be equals to, so I will just start with En. It is n square h phi square pi square by 2ml square, which is L is the length of the box. Now, as we have seen earlier, when we say ground state, now we are not talking first excited, we are saying it is the third excited state. So that doesn't mean n equals to 3 actually. So we know that ground state means n equals to 1. So let me just write this in blue, so that this is important. As we have seen in up to this problem as well, I guess this thing must be clear by now, but let me just write it again properly. So when we say ground state means it is n equals to 1. When we say it is first excited state, it means we are saying n is equals to 2. When we say it is second excited state, we means n is equals to 3. Sorry about that. Okay, so when we say ground state is n equals to 1, when we say it is first excited state, it means n equals to 2. When we say it is second excited state, it means n equals to 3. And now we are saying that we are going to third excited state. We are in the third excited, it means we are saying that n is equals to 4. We are in the fourth energy level. When we say third excited state, it means n equals to 4. And what we have to find, we have found a de Broglie wavelength for our particle, which is in this third excited state. So first we will find the energy of the particle. So first we will find the energy of the particle. That will be equals to, we know third excited state means, okay, sorry. So we know that third excited state means n equals to 4. So energy of the particle will be E4, n equals to 4. So it will be 4 O square times h phi square pi square by 2 ml square. So basically energy of the particle will be equals to 4 square 16, and 16 will be divided by 2, it will become 8. So I will just write the answer, 8 times h phi square pi square by ml square. Alright, so that will be the energy of our particle. Then if we find this d, now we have to find the de Broglie wavelength. So what is the de Broglie wavelength? GLIE wavelength. So what is the de Broglie wavelength when we say? So de Broglie wavelength is basically equals to, is given by h upon p, where p is the, okay, and also let me just write this as well in blue, which I have written this in blue. Again, let me just select this and let me just make it blue. Happen? Okay, it will not happen. Okay, let me just write this one in blue so that it is okay. So this is the definition of de Broglie wavelength, which means if I represent it by lambda, that is equals to h upon p, where p is given by, where p is basically momentum of the particle. Okay, so p is basically the momentum of the particle, and that is how we write the de Broglie wavelength, which is just h upon p, and h is our Planck constant. Now in quantum mechanics, generally, so I'm not sure right now, so I'm just writing it generally. Momentum, so we know there is an operator minus iota h del by del x for momentum, but in generally you can see that in most of the problem the momentum is given by h cross k, and the kinetic energy is given by will be p square by 2m, so it will be h phi square k square by 2m. Alright, especially in our problem in particle in a box, these things are varied. Momentum is given, will be given by h cross of k, the momentum of the particle will be given by h cross k, and the kinetic energy of the particle will be given by p square by 2m, that will be h cross k square by 2m. Now let's go to our problem. So we have the energy of the particle, and we have to find the de Broglie wavelength, and we have all these definitions now with us. Now for particle in a box, in a 1D box, potential energy is 0. Okay, so we know that, okay, when we say this infinite potential, the condition is that V is equals to 0, so there is no potential energy. So the energy of the particle is equals to its kinetic energy, which is given by h phi square k square by 2m. Therefore, whatever whatever En we get for particle in a box problem, that will be equals to kinetic energy of the particle, and that will be equals to h pi square k square by 2m. Alright, so there is the kinetic energy of the particle, it will h pi square k square by 2m. So now this implies our energy, the energy of our particle is E4, okay, that we have calculated to be at 8 times h pi square pi square by ml square. Now that will be equals to h cross square k square by 2m. Okay, from here we can find h cross k whole square. Okay, and that will be equals to 16 times h pi square pi square by l square. Alright, and from here we can find h cross k will be equals to 4 h cross pi by l. Okay, I am not taking plus minus sign, we are just interested in the magnitude. Okay, so this is what we have, and we know that this will be equals to p. This will be the momentum of our quantum particle. Okay, so this is the momentum of our quantum particle. So therefore our de Broglie wavelength which is given by h upon p, this will be given by h upon h cross k. Okay, and wavelength h upon p, h upon h cross k, and h cross k we have found is given by 4, so we have h upon 4 h cross pi by l. Alright, 4 h cross pi by l. So that gives us hl divided by 4h, and h cross is h upon 2 pi. So I will have this 4h pi times 2 pi, and L will go up, and then we can just do the cancelling and all. So what we will get is L by 2. So that means that is lambda. So our lambda de Broglie wavelength is coming as L by 2. Okay, and and for this if we draw our potential curve as well, so basically if we see what is our state actually is, if we draw our state, so basically what we had is the sorry, third excited state. We have n equals to 4, third excited state. So for third excited state, if we draw the third excited for which is n equals to 4, if we draw, so for n equals to 4, the wavelength will the wavelength of our particle will look something like this. Alright, so it will look like this, and here you can see that our particle's wave function will look like this, and this we can see that this is the wavelength lambda, and that lambda is equals to L by 2. So we can see that the wavelength of this wave function that we have for our nth state for e equals to 4, that is equals to whatever the de Broglie wavelength that we have calculated, which is L by 2. Alright, so it is equals to this wavelength. This is for n equals to 4, particle in a box n equals to 4 case. Alright, for this we have this, and this lambda is equals to L by 2, what we got from this is basically this lambda L by 2 wavelength of this wave function, that is equals to the de Broglie wavelength L by 2. Right, so now now we will go to problem number 9. Alright, 8:30. Okay, let me just do it fast. Okay, so in problem number 9, what we have is a particle is confined again in a 1D box of length L. The particle is initially in its, okay, so this is an interesting problem. Okay, so what we have is we have a particle in a 1D box of length L. Now the particle is initially in its 4th excited state. Okay, the particle is in now its 4th excited state, not n equals to 4, so the n will be equals to 5 when you're saying it is 4th excited state, and it makes a transition from its 4th excited state to the 3rd excited state, emitting a photon of frequency nu1. So let me just start the solution, and then we will just go through the problem. So now again we know that our energy En, let us write it again, ny square h pi square pi square by 2ml square, the box of length L only. So this is our energy of each nth state. Now for ground state, and then let me just write that it as n squared times E naught, where E naught is equals to again h pi square pi square by 2ml square. Alright, just to make things clear. Okay. Now again the same thing that we have to keep in mind. Fourth excited state means n equals to 5. Third excited state will mean n equals to 4. Second excited state will mean n equals to 3, and the ground state means n equals to 1. Okay, so that is I guess is clear by this point. Then that what we mean by when you say nth excited state means n plus 1 should be the value. It is okay. So if fourth excited state means n is equal to 5. Okay, so let's see what is given in this problem basically. So okay, so our particle. So let me just make this n equals to 5. Let me just make this n equals to 5. Then we will have some suppression, and we will, okay, let me just make it on now. Okay, so let's say we are at n equals to 5. Then by after subtraction we will have our energy level n equals to 4. Then this okay, someone has tried again. Okay, fine, like this. Okay, yeah, so we have n equals to 5, n equals to 4, then with a little less separation. So I will explain why the spacing I am not keeping equal. So that is what we will see in this problem. N equals to 3, and I will make it a little more smaller, n equals to 2, and then the smallest one, n equals to 1. Alright, so what was our question? So our particle is initially in its fourth excited state, it is in n equals to 5. Then it makes a transition from its fourth excited state to the third excited state, emitting a photon of frequency nu1. Okay, so our particle is in its fourth excited state, it is n equals to 5. Then it makes a transition from n equals to 5. It goes from fourth excited state to third excited state. It means it goes from n equals to 5 to n equals to 4. And during this process, it will emit a frequency mu1. Alright. Here let me write this energy levels. Okay, it emits a frequency nu1, and the energy level that we have is our energy E5, which in terms of E naught will be equals to 5 square times E naught, which is 25 times E naught. E of 4 here is 16 times of E naught. E of 3 that will be equal to 3 times of E naught, which is 9 times of E naught. E of 2 will be 4 times of E naught. Alright, 2 square 4, and E1 it will be 1 square times E naught, so it will be just E naught. Alright, so our first transition happens from n equals to 5 to n equals to 4, emitting a photon of frequency nu1. Alright, and from here we can say that our delta E, so I can say our delta E for this thing, delta E1. So this energy difference, let's say this energy difference is going to be delta E2. Okay, so what will be our delta E1 is going to be? So our delta E1, as we can see, delta E1 is basically just going to be E5 minus E4, E5 minus E4, which will be 25 of E naught minus 16 of E naught. So our delta E1 is basically equals to 9 of E naught. Okay, so we have delta of E1. Now basically we will have so first let us find what nu1 is. Okay, so it goes from n equals to 5, n equals to 4, emitting a photon of frequency nu1. We know the energy difference delta E. Now we know a relation. This relation we need to keep in mind. that delta E is given by h times nu. So if we have energy difference between two states and we have a transition and there is a photon of frequency nu is going, then this energy difference will be equals to the Planck constant h times the frequency of that photon nu. So delta E will be equals to h nu. Then using this, we can write delta of E1 will be equals to h times nu1. Alright, and so from here we will have nu1 will be equals to 9E0 by h. Right, so we have found out our first frequency of the first photon that is emitted, nu1 equals to n times of E0. Then similarly, now after that, then it makes a transition from its third excited state to the second excited state, emitting a photon of frequency nu2. Alright, so what does it mean? It means our particle is now going from third excited state. It means it's going from n equals to 4 to n equals to 2. For n to n equals to 3. Sorry, it is second excited state. It means it is n equals to 3. So now our particle goes from n equals to 4 to n equals to 3, emitting a photon of frequency nu2. And now again, this energy difference we can say delta E2, that we can calculate again. Alright, similarly how we have calculated delta E1. And here you can see that it is just 16 minus 9, it's going to be 7E0. Then let's just complete the diagram. Then what happens? Then our particle makes again a transition from its second excited state to the ground state now. So it has now reached to the ground state, emitting a frequency nu3. So what happened? Our particle went from fourth excited state n equals to 5 to third excited state n equals to 4, emitting a photon of frequency nu1. Then it makes second transition from third excited state n equals to 4 to the second excited state n equals to 3, emitting a photon of frequency nu2. Now it makes a transition from that second excited state, which is n equals to 3, to the ground state directly. It is now going to state, and it is emitting a photon of frequency nu3. Alright, and the energy difference that we are going to have is going to be delta E3. Alright, so this is our problem. Okay, we are going from 5 to 4, emitting a photon of frequency nu1, 4 to 3, emitting a photon of frequency nu2, and then we are going from n equals to 3 to n equals to 1, emitting a photon of frequency nu3. Okay, so if you just follow the question, so this is how you can just convert your question into this kind of a diagram problem, which makes it quite easy. Okay, it does even like these are in excited state and all. So from excited state you go to n and then you make this diagram. So that makes this transition problems easy. So you have these three frequencies, you have this delta E values from which we can find these frequencies, and the question is we have to compare these frequencies nu1, nu2, nu3, and given that the ground state energy is E0. No, ground state energy is given as E0, sorry. So E1 is E0, basically we are also seeing that. Alright, so now again, we have already found nu1. Similarly, we can find this nu2 and nu3 as well. So now our nu2 will also be equals to delta E2. Okay, now our delta E2, again we can find that what will be our delta E2. It will be E4 minus E3. So it will be 16 times E0 minus 9 times E0. So our delta E2 is going to be 7 E0. Alright, so this is going to be 7 E0. So our nu2, that is going to be delta E2 by h, Planck constant. So it will be equal to 7 E0 by h. Okay, so we have found our nu2 as well, and then we will have our delta E3, and our delta E3 will be equals to E3 minus E1. Okay, so that will be equals to 9 E0 minus E0. So our delta E3 will be equals to 8 times of E0, and thus our nu3 will be equals to delta E3 by h, that is equals to 8 E0 by h. Alright, so now we have nu1, nu2, nu3, and on comparing, okay, nu1 is 9 E0 by h, nu2 is 7 E0 by h, and nu3 is 8 E0 by h. So we can on comparison we can say that our nu3 is greater than okay, so our sorry my mistake. Okay, the maximum value is 9 E0 by h, which is our nu1, okay, which is going from n equals to 5 to n equals to 4. Then we have 8 E naught by h, which is our new 3, which is from going from n equals to 2 to n equals to 0. And then we have our new 2, which is 7 E naught by h. Okay. So this is our comparison. The new one is the highest one. Then we have new 3, and then we have new 2. So basically from this problem, this is the way you can solve this transition problems. When you go from this energy state, you just go through the problem. Sorry. Yeah, sorry about that. You just go through the problem and you find this delta E transitions, and from this delta E you can calculate your frequencies, whatever your frequencies are. And okay, so by delta E by h you can find this. And interesting thing that we have noticed is that the energy difference between this energy levels of the energy difference between this energy levels for the particle in a box, that increases with the increasing number of n, and that we know that that we can you can see if you just you can just try to find delta E n comma n minus 1, which will be E of n minus E of n minus 1. You can try it out. Okay, let me just write it in red, so you can try this thing. So you can write delta E of n, and just write it here, just okay. So delta E of n comma n minus 1 will be E of n minus E of n minus 1. And if you solve for a particle in a box, this delta E of n comma n minus 1, if you solve it, it comes at 2n minus 1 times this E naught. Okay, so we can see that this value increases with n. So here we can see that although the transition was from just one state, from n equals to 5 to n equals to 4, the frequency is the energy difference was quite higher, as the frequency of the photon is higher compared to the transition where we go from 2 state, we jump 2 state, we go from n equals to 3 to n equals to 1, because there we jump on in the from higher states, n equals to 5 to n equals to 4. Alright. Sorry, okay, so this is the last question, and then we'll go into the coding session. Okay, we are quite late actually, it's 8:47. Alright, yeah, so this is our last problem for the theoretical section part. Alright, so we have we have a particle in the infinite square well, again particle in a box problem, which has an initial state which is a mixture of its ground state n equals to 1, and third excited state n equals to 4. Okay, so now in this question you don't have to put your brains. Okay, and ground state you are given basically an initial state which is a mixture of n equals to 1 and n equals to 4, and it is given by some 1 by root 3 times psi 1 plus root 2 by root 3 times psi 4. That is our initial ground state. Now the ground state energy we are saying it is denoted by E naught. Now the first question that is being asked is, what is the expectation value of energy? This. Okay, so the expectation value of energy, first we have to find the expectation value of energy. So that is given by this expectation value of energy, you can write it as psi h cap psi. So this is a bracket notation. So this is a bracket notation. So please bracket notation. So this is really important in quantum mechanics. Like if you use this bracket notation, that makes it really easy. So here basically you can see that what I have written this in this consigned form, this psi h cap psi. Okay, so that is basically giving me, that is basically 0 to L, where our particle remains, let's say length of the box 0 to L, psi star of x h cap, our Hamiltonian, times psi of x dx. Okay, so basically the psi h cap psi is showing gives you this integral. Okay, and I will try, if you guys want, please let me know in the in the discussion forum. So I will include a link for this for some tutorial on this bracket notation, because they are very important in quantum mechanics, and it will really help you in solving a problem fast. So for this problem, okay, and also remember that h cap psi 1 will give us E1 times psi 1, and h cap psi 2 will give you E2 times or if I say, okay, so that will be equals to E1 times psi 1, or I can say E1 is here E0, so it will be E0 times psi 1, and now my h cap acting on this psi 4 will give me E4 times psi 4, which will be 4 is 4 square 16, so it will be 16 E0 times psi 4, and I can write my psi, my initial wave function psi that is given, I can write it as C1 times psi 1 plus C2 times psi 4, where C1 is basically 1 by root 3 and C2 is under root of 2 by 3. Alright, so this is how we write. And if we have to find this expectation value, so we know this is basically psi h cap psi. Now this you can write as C1 times psi 1 plus C2 times psi 4 h cap C1 times psi 1 plus C2 times psi 4. So this you can write it as C1 square psi 1 h cap psi 1. So this is bracket notation, so maybe many people might not know it, but I guess you can write this form in this integral form as well, and you can check that how this bracket notation works. And I will also try to put some tutorial video on this bracket notation in the disclaimer, not mine, maybe if there is some, there are many videos on YouTube, so I will try to find some good tutorial video and maybe do a brief tutorial in some of the next sessions. So here you can just calculate it, C1 square psi 1 h cap psi 2, then you can have C1 C2 psi 1 h cap psi 4 plus C2 C1 psi 4 h cap psi 1 plus C2 square psi 4 h cap psi 4. Then I'm going to skip some step because okay, we are really at 8:50 already, we are not in the coding part now. Okay, so here we can see that h cap acting on psi 1 will give you E1 value, so this will just give you E1 times C1 square, okay, times let me just do it once, okay, and this h cap acting on psi 4 give you E4 C1 C2 times psi 1 psi 2, plus we will have C2 C1 times h cap acting on psi 1 will give us E1 psi 4 psi 1, and we get C2 square psi, what we get here, E4 psi 4 psi 4. Okay, and we know that these solutions of particle numbers, they are orthonormal to each other. So what will happen is this will be equals to 1, this will be equals to 0, this will be equals to 0, and this will be equals to 1, since size are orthonormal. Okay, so basically what this gives us is that this h cap average of this is the, okay, h cap I should have noted that, okay, this h cap is basically expectation value of energy, expectation value of energy is given by this. H cap is our Hamiltonian, so that will be given by E1 C1 square plus E4, okay, from here it is E1 C1 square plus E4 C2 square. Okay, so this, if you remember this also, that will work. So for any question, if you have given initial state as a mixture of two states, then the average energy, expectation value of the energy, will be given by the energy of each state multiplied by the coefficient square. Okay, so this is important, this you should remember. If you don't understand this bracket notation, you can just remember this. So from here our h cap expectation value will be equals to E1 is basically E0 and C1 is 1 by root 3, plus it will be 16 E0 times under root 2 by 3, that will be 2 by 3, and our expectation value from here h cap will come as 11 times E naught. So you can just solve and find it is E naught by 3, 16 or 32, 32 plus 1, 33 by 3, it is 11 E naught. Alright, now let us go to the B, C and D part. So in B part it is asked that if you do a single energy measurement, what would be the outcome? Now if you do a single energy measurement, so what will happen is that this wave function, which is a mixture of two state, it will collapse to any one of these state. Alright, so it will collapse to any one of these state. So we are going to get a value of any one of this energy state. Okay, so in B, so for B basically we will either get the energy of the ground state, which is the E naught, or we get the energy of the third excited state, which is going to be 16 times of E naught. So in a single measurement, the wave function would collapse to either psi 1 of x or psi 4 of x. Okay, so our wave function will either collapse to psi 1 of x and psi 4 of x. Okay, so the measured energy. Okay, so this session I am going to extend by 30 minutes because I have to complete the coding part as well. So sorry about the session went wrong. So the measured energy would be either E naught or 16 times of E naught. Okay, so it will be either n equals to 1 energy, it will be E naught. E naught is basically E1, or it will be E4. Okay, n equals to 1 or n equals to 4. Okay, and so it could be either one of them. Okay, when we do a single measurement, but then what is the value of the C1 C2? But C1 C2 still gives us some probability, so we can say that with probability with E naught, with getting E naught by probability one by 3, which is C1 square and getting 16 E naught by probability two by 3, which is C2 square. Alright, so we can get any of these two values when we do a single measurement, but we can say that okay, by probability 1 by 3 we will get either E naught, and by the probability 2 by 3 we will get the 16 E naught. Okay, now comes the interesting part. Now the interesting part is question number part C. So now instead of doing a single measurement, what we are going to do, we are doing a very large n number of measurements, but there is a catch. What we are doing is that after every measurement we are going back to our initial state. Okay, that is a really important part. Okay, so that is a really important thing that we need to keep in mind, and we will see in part D why this thing is why this is very important. Okay, so now instead of doing a single measurement, we are going to do n number of measurements, considering n to be a very large number, and for after each measurement we are going back to our initial state, which is this combination 1 by root 3 psi 1 plus 2 by root 3 psi 4. Then what would be the outcome? Okay, now what would happen is that since we know that we are either getting E naught value or the 16 E naught valued by the probability 1 by root 3 and by the probability 1 by 3 and 2 by 3, and now we are considering that there are very large number n values. So we will so now this probability will have, we will see its effect. So now what will happen is the so the number of times energy outcome is E1 equals to E naught is given by, so that will be given by C1 square times n. Okay, since n is very large, now since n is very large, now we can say that the number of times the energy will happen, so we can say n is like million times or something. So there will be, then you will start seeing the probability. So it will be, although I can't say it is going to be exact because they are still probability, so you can say okay, it will be approximately C1 square by n, and C1 we know is 1 by root 3, so n by 3. So approximately I can say that n by 3 times I'm going to the outcome of the energy will be E naught, even value, based on the probability. Okay, so for n very large, so like if it is like thousands or millions, so we can say that this. Okay, so why this is happening, let me just write that here. The wave function will collapse. Okay, the wave function will collapse to either psi1 of x or psi4 of x with probabilities given by C1 square and C2 square respectively. Since n is very large, the number of outcomes with each outcomes with a specific energy value is given by n times the probability of getting that outcome. Okay, so that's why we are saying that number of times energy outcome will be E naught, will be C1 square n, will be the n by 3. So it will be probability times n, which is a very large number. Now that we are saying 3, and similarly the number of times energy outcome is E4 equals to 16 E naught is given by, again I say approximately C2 square by n, which will be equals to 2n by 3. Alright, so based on this probability, if we do a very large number of measurements, n number of measurements, then we can say that n by 3 times we are going to see, we are going to observe energy E naught. And the catch is that after each measurement we are going back to the initial state. Okay, so that's the catch. Okay, after each measurement you will go back to your initial state, which is a mixture of this with those C1 and C2. So if we do an experiment like this, we measure the thing and we go back to the initial state again and again, then n by 3 times we are going to measure the value E naught, and 2n by 3 times we are going to measure the value 16 E naught. Okay, so that's the difference between doing a single measurement and then doing an infinite number of like a very large number of measurement, or you can say infinite number of measurements, something. All right, but the catch, but the catch is, the main part is that you have to go back to the initial state after each measurement, and that comes into this D section, into the D part of the question, Then the question is asking like, what would happen if you don't go to the initial state after each measurement in part C? So that's the catch. Okay, so like if you are doing n measurements, but instead of going back to your initial state, you are just continuing your experiment. Like you just measure you just measured you did your first measurement, and you just continue whatever you got. You just continue your second, third, and go on with that n measurements. So is the outcome is going to be the same as we observed in part C? So the answer is no. So what will happen is that when we measure our system, which is right now is a mixture of psi1 and psi4, and we measure it as we have seen as soon as we measured it, the system collapsed to one of the states. It will either collapse to psi1 and psi4. And now when it has collapsed, now now if you do the second measure on that system, then it will give us the collapsed wave function psi1 only. So our outcome will always be going to be E1 only. So we are always going to the outcome will always going to be E0. Alright. So that's the case. So in D we will not observe it. So basically again it will become, the answer will be similar to what you will get in a single measurement. Now you are doing n measurements, but your answer will be whatever you get from a single measurement. So maybe you will get in your first measurement, you might by some probability 1/3 you will get a measurement E0, and now you're not going to back to the initial state, so you just keep measuring 1000 times or 1 lakh times the value, or million times the value that you will measure will be E0, because your wave function has now collapsed to psi1. Or if you have somehow you by probability 2/3 in your first measurement you get the value 16 E0, then now you can measure billions of time to that with that wave function. You can just keep measuring, the value will be around 16 E0 only. You're never gonna find E0 value, because your wave function has collapsed, and now you are not going to that initial state. Okay, so that was the catch in part C, that we have to go back to the initial state. Alright, so let me just write it down. So if we don't go to the initial state, then wave function will collapse to either psi1 or psi4 in the initial measurement, and will remain in the same state for the rest of the experiment. So we will either measure E0 for all n measurements, with a probability of 1/3, or we will measure 16 E0 for all n measurements with a probability of 2/3. Alright, and this is also happening because every operation, every the measurement that we do, then in quantum mechanics they be represented by operators. So since every thing will commute with itself, so if we do the same operation again and again, then it will not change the state. Okay, the system will remain same. And there is a concept of commutation of operators. So maybe instead of measurement, if you do something else as well, and if the operator of that measurement commutes with the Hamiltonian, then also the state will not change. So so for that I will refer you to Introduction to Quantum Mechanics by David J. Griffiths. Okay, so this is a very nice book for the beginners in quantum mechanics. मोबाइल ले आओ ना, मेरा काम 10 बार बंद कर दो। उसको एक बार बंद कर दो ना, राइट साइड कर दो ना। नहीं, आप राइट साइड नहीं करते हो, आप लेफ्ट कर रहे हो। Okay, sorry about it. Okay, so this is the reference that I recommend, Introduction to Quantum Mechanics by David J. Griffiths. Okay, and for this problem, which I discussed the C and D part, look about commutation of operators. Alright, so for this part, look for the computation of operators section, so I guess you will understand much better. Alright, so now we will go back to our coding session, and I am extending this session by just 30 minutes just to finish this coding part. Okay, so yes, it is quite delayed. So we are going to, in this session we are going to do a Python tutorial, small Python tutorial, and also this infinite square well, symmetry potential as well. Yeah, I guess we have to skip this infinite square well potential this time. So in the next session I will start from this infinite square well and the Python code. So in the next 20 minutes yeah, I will just do this Python tutorial that I have made, so that which will help you with your assignments and the course. And in the next session I will continue this with this infinite square well symmetry potential. Let me just go here and stop sharing. And let me just share my. Alright. Alright. So okay, so this is the Python tutorial. This is the link to see the documentation of NumPy. You can go and look at this one. Alright, so let me just yeah, I guess the session is already too long. Let's slowly. Okay, sorry, this is not the first session. Okay, this is the first session. Okay. Okay, the session is already too long, so I guess I have to stop it. Unfortunately the time is extended already. It is 9:13 p.m. so I couldn't go to the coding section part in this session. So in the next session, just 1 minute. Sorry everyone, what I was saying is, okay, yeah, so we have we have already extended this session. Is 9:15 p.m. So unfortunately I could not go to the coding section of in this tutorial session. So in the next tutorial session we will start the basics of the Python. Okay, so we will start with the basic Python tutorials of NumPy and Matplotlib, and then the problem of this infinite square wave with symmetric potential. So 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 in the next session we are going to do that coding part, because already we are it is quite like 9:15 p.m. and I won't be able to solve this. Okay, so in the next session we will start with the Python tutorial, and then the problem of the infinite square well with the symmetric potential. Okay, so thank you all and goodbye. Hello. Okay, thank you.